We just derived the derivative of e raised to some function g of x. But what if our base is not e? There are exponential functions where our base is not e. So let's say we had y is equal to a raised to the x piece, where a can't be 1. A has to be greater than 0. If it was negative, it would be bouncing back and forth between positive and negatives, and that's not an exponential function. And right now, we're just saying that a is not going to equal e because we already know what that derivative is. So let me give you, before we look at the derivative of this, we need to manipulate this into something that we know how to do. And so I need to give some rules, or we call rules of logs, logarithms. And so recall, if you have a raised to log base a, so of y. If our base is the same as the log base, and that is in the new exponent, this is equal to y. Okay, so let's take the natural log, first of all, both sides of the equation. So I can take the natural log of both sides of the equation. If we do something to one side of the equation, we do it to the other. So the natural log of y is equal to the natural log of a raised to the x power. Well, I want to have the same base, natural log of x. This is the same thing as log base e of x. We just write it as ln. That's an L, it's not a 1. So ln. So let's look at this and rewrite it. And so if we do that, we want to take e raised to the natural log of y equals e raised to the natural log of a raised to the x power. Doing the same thing on each side of our equation. And then there's another rule of exponents, or rule of logs. If you have some log base b of something raised to a power, that's something that power can be rewritten as coming down in front. So this is the same thing as x times log base b of a. So I want to use that rule that I just said and take this and bring it down in front of my natural log. Well, this e to the natural log of y, and that's just y, so I can just write that as y, equals e to the x times the natural log of a. Well, we just learned how to take the derivative of e raised to some function of x. And so now we can take the derivative of both sides. So dy dx, this is equal to, okay, so the derivative of our exponent. So d dx of x times the natural log of a times the original e function itself. So times e raised to the x natural log of a. Okay, so the derivative of x times the natural log of a. Well, the natural log of a is just a constant. It's some coefficient, some number. It's not a variable. And so all we're doing is taking the derivative of x, which is 1, times that coefficient natural log of a. So the derivative of x times natural log of a is just the natural log of a. And let's rewrite this e piece. Let's move this exponent back up as a, this x in front back up as an exponent. So we can rewrite this as times e to the natural log of a to the x. Well, going kind of backwards, same base here. This is e, this is natural, this is log base e. So this is the same thing as a to the x. So this right here is just a raised to the x power. And let's bring down the other piece in front, natural log of a. dy dx. So we just came up with a rule. If y is equal to a raised to the x power, those, again, rules have to hold. A can't be 1, a has to be positive, and in our case, you can leave it as e if you want, if it was e, but the rule says that dy dx, or the derivative d dx of a to the x, is equal to the natural log of our base, a, times the original function, a to the x. If it was e, well, the natural log of e, if you remember rules of logs, this is saying, if I round it as log base e of e, this is saying e to what am I going to raise my base to? What is my exponent on e to get back this e? Well, my exponent of e would have to be 1 to get back e. So let's just look at one example really quickly, and then we'll take a break. I see one. So before I pull in an example where a base is not e, let's kind of talk about the rule if our function, our exponent was a function. So let's say it was y is equal to a raised to the g of x power. It's kind of similar to the e. So basically, it's the derivative of our exponent. So the derivative dy dx is equal to the derivative of our exponent, g prime of x, times the derivative of our original function, a g of x. And the derivative of the original, I'll just do it, is, as we saw, was times the natural log of our base, a, times the original, a g to the x. So if we had, let's say, y is equal to 4 raised to negative 5x plus 2 power. So our exponent, take the derivative of this, dy dx. This is equal to the derivative of our exponent, d dx of negative 5x plus 2, times the natural log of our base, which is 4, times the original function itself. The original function itself was this 4 raised to negative 5x plus 2 power. So derivative of negative 5x plus 2, that gives us derivative of negative 5x is negative 5. Natural log of 4 times 4 raised to the negative 5x plus 2. We're going to keep it like this. We cannot multiply the negative 5 and the 4 together because the 4 is raised to some other exponent than 1. And so that's our derivative when our base wasn't e. Okay, so we pulled up, or I just pulled up the derivatives of the exponential functions. So, and these are what we've been working with. And we have the derivative of e to the x, we know is just e to the x itself. This is written a little differently than how I had written it, but that's just saying the derivative of e to the u is e to the u times the derivative du dx. So that's saying the derivative of u. So I had written as d dx. Well, I had written it a little differently than that too, but they all mean the same thing. E to the gx is the same thing as taking the derivative, g prime of x, of the exponent times the original function itself, e to the gx. But these are equivalent. So same thing with a base other than e. I guess this works too with base e. It's just that the natural log of e is 1. So the derivative of a to the x is its original function, a to the x times the natural log of the base. And the derivative of a to the u, where u is a function of x, is its original function times the natural log of the base a times the derivative of our exponent, where I had written it as d dx of a raised to the g of x power. This was equal to the derivative of the exponent, g prime of x, times the natural log of the base, a, times the original function itself, which was a g to the x. But again, it's equivalent to that, just written a little differently. So I'm going to not jump into taking derivatives of logarithms. I'll wait until after you take the test next week. So when you do your homework assignment where you're looking at taking an old exam, sorry, trying to do 2 things at once. Ignore the one question, I believe, that has a log in there, finding the derivative of that log. You won't have to worry about that for this test coming up next week. So in front of you, we have an example, e to the x minus e to the negative x all over x, and we want to find the derivative of that function. So find dy dx. I notice in here, I'm going to have to use the quotient rule. And so using the quotient rule, taking the derivative dy dx, we would look at the derivative of our numerator. So let's just write that we're doing that, d dx of our numerator, e to the x minus e to the negative x, times the denominator, times x, minus the numerator. So e to the x minus e to the negative x, times the derivative of the denominator, d dx of x. And this is all over our denominator, which is x, quantity squared. So let's go through and take the derivative of e to the x minus e to the negative x. Derivative of e to the x, well, derivative of e to the x is just itself, e to the x, minus, so derivative of e to the negative x, that's a little different than e to the x. And so we're going to take the derivative of a negative x, which is negative 1. Take the derivative of the exponent times itself, e to the negative x. All times the denominator x minus the numerator, e to the x minus e to the negative x, times the derivative of x, which is 1. All over this quantity squared. So I noticed there was a question, so let me just pause and I'll see. Okay, so there was a question on what rule we were using, and then we're using the quotient rule. And within the quotient rule, we're using the chain rule on this piece. And so let's look at this and clean it up a little bit. So right here, in the first parentheses, we have e to the x minus a negative, so plus e to the negative x, all times x, minus, well, we could, if we wanted to distribute this negative, I don't know if that would help. Well, let's do that. Let's distribute that. No, I won't. Well, let's just do it. E to the x plus e to the negative x, all over this quantity squared. I noticed that we don't have anything really in common that I could pull out or factor out. So I might distribute this x in here. There's nothing I could combine once I do that. So it's not like I can simplify it much more. So if I distribute the x, we'd have x e to the x plus x e to the negative x minus e to this x plus e to the negative x, that quantity, all that over x squared. Okay, so we found the derivative of that. Okay, so our next example, we have f of t equals the quantity e raised to the t squared power plus 5t. That whole quantity is cubed, and we want to find the derivative. So I noticed that we have multiple places where we have the chain rule that needs to be used. So if I'm thinking of this, I have an outer function in here. So an outer function, I don't know, let's call that g of t. So my g of t function would be t cubed. If I take the derivative of this, let's just do it right now, g prime of t, that right there is, bring our power down front, 3 times itself. Sorry, not times itself. I'm used to saying that with the e. Bring our power down front and then subtract 1 from our exponent. So this is 3t squared. Our inner function, maybe call it h of t. H of t, that's the e to the t squared power plus 5t. So let's take the derivative of h of t. H prime of t. Well, the derivative of e is the derivative of the exponent. So if I look at the exponent, derivative of t squared, maybe I'll just write that for now, d dt of the exponent t squared times the original function, which is e to the t squared, plus the derivative of 5t, which is just 5. So the derivative of h prime of t, this is equal to the derivative of t squared, which is 2t, times the e itself, e to the t squared, plus 5. One of our notations that we did for the chain rule was if we had some function, and our function right now is called f of t, f of t could be rewritten as the composition of g and h of t, where g was the outer function, h of t was the inner function. And when we took the derivative of f of t, the rule said for the chain rule, we take the derivative of the outer function, keep the inner function the same, times the derivative of the inner function, h prime of t. So we pretty much did all our work already. Let's just put it together. So the derivative of f prime of t, it says, is the derivative of the outer. Well, we found the derivative of the outer. So that is 3 of the inner function now. So this is 3, let me just leave it like this, 3 h of t, and then it was squared, times the derivative of the inner. So the derivative of the inner was 2t e to the t squared plus 5. So this is equal to 3 of the inner function. Our inner function was this e to the t squared plus 5t, quantity squared, times the outer, times the inner, derivative of the inner, 2t e to the t squared plus 5. So really, I normally, if it helps you at first to break it down, you can do that. As we move on, I really don't do that. I would start with this right here. F of t equals this e to the t squared plus 5t cubed. I would notice right away what my outer function is. So if we have some parentheses raised to the power, that inner or the outer function is going to be what that parentheses raised to the power. So I would see right away that we can use the general power rule. Let's bring the 3 down front. Of the inner, keep what's inside the same. E to the t squared plus 5t. Subtract 1 from our power. So 3 minus 1 is 2. Times, and this is where I might just say I'm going to take the derivative of the inside and then do it. So d dt of the inside, e to the t squared plus 5t. And then jump down and just take the derivative of this really quickly. So, and we've already done that work. So I just kind of wanted to show how I normally would walk through this with you guys. And maybe we should do a couple more like that. Okay, so this one looks good too because it uses a lot of different rules. Let's say you have e all raised to the x times the square root of 3x plus 2. And this is f of x equals. And we want to find the derivative of f of x. So let's look at this. It's the derivative of e. So let's just write that, what the rule says. It says for a derivative of e, it's just the function itself times the derivative of the exponent. So let's just write that we're going to take the derivative of the exponent, d dx of x times, I noticed that when we have that square root, we had to rewrite our radicals as without the radical and with exponents. So this square root we call of 3x plus 2. And this is the same thing as parentheses 3x plus 2 all raised to the 1/2 power. So let's just rewrite that. So that's times that 3x plus 2 all raised to the 1/2 power. So that's the derivative of our exponent, which we haven't done yet, times the original function. And the original function is e raised to the x times square root of 3x plus 2 power. Okay, so when we come in and we take the derivative of the exponent, notice that we have to use the product rule. And within that product rule, when we take this, the derivative of what was the square root, we're going to have to use the chain rule. So looking at the derivative of the exponent, now I'm going to just write it out. So in this piece, we have bracket, the derivative of x, which is, let's just do that, 1 times the second function, which is 3x plus 2 to the 1/2 power, plus the first function, which is x, times the derivative of the second. So if I take the derivative of the second function, I need to use the chain rule. So let's bring our power down front, 1/2 of the inside, 3x plus 2, and then subtract 1 from our exponent, 1/2 minus 1. 1/2 minus 1 is negative 1/2, times the derivative of the inside. So derivative of the inside, let's just write that for now, d dx, and the inside, 3x plus 2. And that was the derivative of the exponent times the original e function, e raised to the x times the square root of 3x plus 2 power. So as we do this, let's kind of clean it up. So as we rewrite this, so looking at this first grouping, instead of rewriting it with a 1/2 power, I know that's the square root. So 1 times, so this is the square root of 3x plus 2 underneath the radical, plus, so I have a negative exponent. I'm going to rewrite this by bringing it down to the denominator and making the exponent positive. So I have an x in the numerator from this x. You can think of that over 1 if you want, all over this 2. And when I make this exponent positive, this is the 1/2 power, the same thing as the square root of 3x plus 2. Times, let's take the derivative of 3x plus 2. Derivative of 3x is just 3, and the derivative of 2 is 0. So it would be times 3. I'm going to put the 3 in front. So that was the derivative of the exponent, all times the original e. So e raised to the x times 3x plus 2 power. So there's the derivative of f of x. So you can see where you needing to know all these different rules and being able to put them all together, like the product rule, the quotient rule, the chain rule, derivative of e's.